Complete the truth table for this 2-input NAND gate. Now we know that for a NAND gate, this is an AND gate, right? It's an AND gate. So for an AND gate, the output is only 1 when both the inputs are 1. And the NAND gate is the exact opposite, right? So when the AND gate gives an output of 0, the NAND gate is going to give an output of 1. 0, 1, 0, 1, and where it is 1, we're going to get a 0 here. Complete the truth table for this 3-input NAND gate. For this, let's quickly take a look at a 3-input AND gate. So here we have a 3-input AND gate, and we can see that the output of this AND gate is only 1 when all the inputs are 1. So when all the inputs are 1, that is the only place where the output is 1. And remember, the NAND gate is the exact opposite. So at all of these places, the NAND gate is going to give us a 1. And in this final row where all the inputs are 1, that's where the NAND gate is going to behave the exact opposite way, and it's going to give us a 0. So our solution is pretty simple. We're going to get all 1s here, just the opposite of the AND gate, right? And this final row is going to be a 0. So now we have a SR flip-flop that has been constructed using 2 NAND gates, and we're supposed to complete the truth table. Okay, let's take a look at the truth table. He's telling us that initially S is 1, right? So S is 1 and R is 0 and Q is 0 and Q bar is 1. Okay, so that's the initial state. And then he's saying that R is changed to 1. What's going to happen now? So if R is changed to 1, this input becomes what? 1. Okay, let's see what's going to happen now. When R becomes 1, you see what we have here is we have 0 at the output here, right? And this 0 is being fed back. There's a feedback here, right? Through this wire as an input here, right? So we're getting a 0 here. So basically we have a 1 and a 0 as the input to a NAND gate. And remember, the truth table for a NAND gate, let me just quickly draw the truth table for a NAND gate. It is the exact opposite of the AND gate. Okay, as we can see here, when we have 1, 0 as the input, right, then the output is going to be 1, which means what? For this NAND gate, we're going to get a 1 here because the input is 1, 0. And we already had a 1, so this doesn't change, so Q bar doesn't change, right? Q bar stays the same, and this 1 is being fed back here to this input. So now we have a 1, 1 here. So S is 1 and the second input is also 1. When both inputs are 1, the NAND gate is going to give a 0 here, which means what? We're going to get a 0 here at the output, and once again the 0 is going to be fed back. And we can see that the system has become stable. Once again we're going to have 1, 0 at the input, and obviously we're going to get a 1. So this system is stabilized, right? So what we have now is that Q stays at 0 and Q bar becomes, and Q bar stays the same, right? Q bar is also 1. Okay, so now we're going to take a look at this situation, right, where the value of S is changed. Remember, previously the value of R was 1 and the value of S was 1, right? And this is what we got, right? So we had Q at 0 and Q bar at 1. So from this state, the SR flip-flop is now going to go to this state, right, where the value of S is changed to 0. So this 1 is now changed to 0, and let's see what's going to happen. Okay, see, this 1 is being fed back here. So that means we're going to have 0, 1 at the input. When we have 0, 1 at the input, the output is going to be 1. And this 1, so previously Q was 0 and now it has become what? 1. And this 1 is now going to be fed back to this NAND gate, and when we have 1, 1 at the input, the output is going to be 0. So this output is going to become 0. So Q bar is going to change. So now we have to, because it has changed, we have to go back and feed it once again to check, if it is going to make a difference. So now we have, instead of this one, we have a 0 here. Okay, so now the input has become what? 0 0. And when it is 0 0, the output is going to be what? When the input is 0 0, the output is 1. So the output stays the same. So we have 1 here. And once again, this one is being fed back, and the input is 1 1, which is same as the previous input. So no difference. So this is going to stay at 0, right? Therefore, now the flip-flop has stabilized, and we can say that the value of Q is 1 and the value of Q bar is 0. Okay, so this is what we have at this stage, right? At this stage, right? So when S was changed to 0, right? So we had Q at 1 and Q bar was 0, right? This was what we got. This was the end result. And now from this stage we are going here, right? And S is once again changed to what? S is changed to what? S is changed to 1. So this is going to get cancelled. We get a 1 here, and let's work out the situation. This Q bar, this value 0 is being fed back. So we have 1 0 at the input, which means what? We're going to get a 1 at the output. We get a 1 at the output, which is the same as Q, right? Q was previously 1, so it stays 1. So Q doesn't change. So now we are feeding 1 here, right? And now we have a 1 1 at this input, right? 1 1. And when we have a 1 1, the output is going to be 0, right? Which means what? We're going to get a 0 here, and it's the same as this, right? And let's just try and feed this 0 back and see if this brings a change. When this 0 goes back, we once again have 1 0, and the output is going to be 1. And so the system is stabilized. Even if we feed this 1 back, we're once again going to have a 1 1 here. So the system is stabilized, which means what? Q stays to be 1 and Q bar stays to be 0. So this was what we achieved. This was what we had, the flip-flop, when this was the last action that was taken, right? I just want to show you, even though it's not required as part of the truth table, I just want to show you what happens when both S and R are changed to 0. When both S and R are changed to 0, so S becomes 0 and R becomes 0, right? And remember, Q was at 1 and Q bar was at 0. Q was at 1 and Q bar was at 0. Let's see what's going to happen. Let's start here. We can start anywhere, but let's just start here, okay? So this 0 is being fed back, right? And we have a 0 0 at the input, which means what? We're going to get a 1 at the output. So we're going to feed this 1 back, and this becomes what? This becomes 1 0. When this becomes 1 0, 1 0 means what? We're going to get a 1 at the output, right? So we're going to get a 1 here. So previously it was a 0, and now it becomes what? A 1. So this 1 is now going to be fed back, and now we are going to have what? A 0 1 at the input, and 0 1 at the input is going to give us a 1 at the output once again. Okay, so when we get a 1 here, we feed this back, and once again, now this is 0 1, it stays the same, right? Because this 1 is being fed back. We already had a 1 here, right? So no changes here. So this becomes 1 and this becomes 1 also. Now this is an unstable state. Remember, Q should be opposite to Q bar. Q should be 1 and Q bar should be what? 0. These two should be opposite, but they become the same. So that's a problem, right? Q and Q bar, should be complements. They should be opposites. But in such a situation, when S and R are both changed to 0, the flip-flop becomes unstable. Q and Q bar both have the same values. So the next question is an obvious question, which says that the final row in the table in part 1, this is the final row, right? shows that the output for both Q and Q bar is 1. Remember, we just discussed this, so this is a problem. Explain why this is a problem. Why are both of these, when both of these are 1, why is this a problem? And this here is the answer. Because Q and Q bar have the same value, that is something that is wrong, because Q and Q bar should be complements of each other, which means what? When Q is, let's say, 0, Q bar should be 1. They should be the opposites, right? So they should be complements of each other, and the flip-flop becomes stable. So this is the answer. Okay, now we have a JK flip-flop, and you can see that in a JK flip-flop we have a clock here, and basically this clock gives a pulse, right? And when this clock gives a pulse, that's when all the inputs are being fed to the NAND gate. So when this clock pulse comes, that's when all the inputs are being fed to the NAND gate. So the basic purpose of the clock pulse is to synchronize the inputs, right? And by synchronization we mean that all the inputs are fed at the same time to the AND gate. So this clock is being used for synchronization. Additionally, if you were to look here at this part of the JK flip-flop, then this looks exactly like the SR flip-flop. So the JK flip-flop is a modification to the SR flip-flop. So JK flip-flop is a slight improvement on the SR flip-flop. Alright, so now let's take a look at the truth table. This is the row in the truth table that we're supposed to complete. The value of J is 1. The value of K is 0. The clock pulse is 1. So if this is 1, that means 1 is being fed here and 1 is being fed here, right? And the initial value of Q is 1 and Q bar is 0. So Q is 1 and Q bar is 0. So let's try and work this out. See, let's start with this one. We can start with J or K, but let's start with K, right? And we can see that this output from Q is being fed back here, right? So we're getting a 1 here. Okay, so this is a 3-input NAND gate, and for this 3-input NAND gate, we have 1 1 0 as the input. And remember, let's just quickly take a look at the 3-input NAND gate truth table here. Only when all the inputs are 1, that is the only time you're going to get a 0. Otherwise you'll always get a 1. Okay, we'll just keep that in mind. So now we have 1 1 0 at the input, which means what? We're going to get a 1 at the output here. And let's take a look at this one. Q bar was 0, so 0 is being fed back, right? So we have a 1 1 0 here, 1 1 0 here, which means what? We're going to get a 1 here. Okay, now we've come to the SR flip-flop. So this is 1, this is 1, and remember this Q is being fed back here, right? This Q is being fed back, so we get a 1 here. So when we have a 1 1, we're going to get a 0 here. And when we and Q bar was already 0, so this 0 is being fed back, right? And we have a 1 0 here, which means what? 1 0 would give us a 1 here. And when we feed this 1 back, we can see that this is already a 1, right? We previously had 1 here also. So the state of Q is not changing and the state of Q bar is not changing. So the system is stabilized, right? What we get here is that Q becomes what? Q stays 1 and Q bar stays 0. Remember, this was the initial stage, right? And compared to this initial stage, we have the final stage here, which is the same. Let's take a look at the next row here, 1 0 1. So J is 1, K is 0, J is 1, K is 0, and the clock is 1, right? So the clock is 1, right? And what about the initial state? Q is 0 and Q bar is 1. So Q is 0 and q bar is 1. Let's try and work this out. So let's start with q bar, for example, right? We could have started with q, but we're starting with q bar. Doesn't make any difference. Q bar is 1, so which means we're feeding a 1 here. When all the inputs are 1, then the output is going to be 0. And let's take a look at this one. Q is being fed back, right, to this input, which means 0 is being fed here. When we have 1 double 0 at this gate, we're going to get a 1 here, right? Okay. So now let's take a look here, right? This output, which is 0 right now, is being fed back to this gate, right? So we have a 1 0 at the input. When we have a 1 0 at the input, we're going to get a 1 at the output. Previously it was 1, and even now we're getting 1, right? So this 1 is being fed back, right? And we have a 1 0 here also, right? When we have 1 0 here, we're going to get a 1 at the output, right? Which means what? Q was previously 0 and it is now changed to 1. Because it has changed, we're going to feed it back. So Q becomes what? 1, right? And we have a 1 1 here. When we have a 1 1 here, what's going to happen? When we have a 1 1 here, the output is going to be 0, right? So the Q bar was previously 1, but it is now changed to 0. So we need to feed this changed value back here. This becomes what? 0. So now we have a 0 0 here, and a 0 0 would give what? A 0 0 would once again give us 1. We feed that 1 back, and this is 1. So because this did not change, we shouldn't actually try and work it out, because it hasn't changed now. We don't need to feed it back. It's the same as the previous value. So even now we have 1 1 at the input, and the output is going to 0, is going to be 0, and previously it was 0, now it stays 0. So we actually understand that the system is stabilized, right? Which means what? Which means that the final value of Q is going to be 1, and the final value of Q bar is going to be 0. So this is going to be 1, this is going to be 0. Now we want to work out this third one, where J is 1, K is 1, and the clock is 1. So J is 1, K is 1, and the clock is 1, which means this is 1 and this is 1. And as far as the initial state is concerned, we have a 1 0. Q is 1 and Q bar is 0. Okay, let's try and work this out. Let's start with Q, for example, right? Q is coming down here and being fed here, which means what? 1 is being fed here. When we have all 1s at the input, the output is going to be 0. And Q bar is being fed back here, right? When Q bar is being fed back, that means we are giving a 0 here. When we have 1 1 0 at the input, we are going to get 1 at the output. And let's try and work out these feedbacks. So we have a 1 here, which is being fed, right? This was a 1, Q was 1. So now we have 0 1 at the input, which would give us a 1 at the output. Let's feed this 1 back, right? And we have a 1 1 here. And 1 1 is going to give us what? At the output, it's going to give us a 0. So this has changed. Because it has changed, we're going to feed it back. Okay. So we have a 0 here. Now that we have a 0 0, the output is going to be what? 1, right? And because it is 1 and it was previously 1, right? That means we don't actually need to feed it back, because it was previously 1 and it is now 1 also, right? So even now when we feed it back, it's still going to be 1 1, and 1 1 is going to give us a 0. And when we feed this back 0 back, we once again going to have a 0 0. So the system is stabilized. So the final values are Q is 0 and Q bar is 1. So Q is 0 and Q bar is 1. Let's try and work out this final row, where once again J is 1, K is 1, and the clock is 1. So J is 1, K is 1, the clock is 1, right? And we have what? The initial state is what? The initial values are Q is 0 and Q bar is 1. So this is 0 and Q bar is 1. Okay, let's start with Q bar this time. We go back and feed this here, which means 1, Q bar was 1. So we have 3 1s at the input, which means what? We're going to get a 0 here, right? And let's feed Q back, right? when we feed Q back here, and Q was 0, right? When we feed Q back here, 110 at the input means what? We're going to get a 1 at the output. Okay, so let's work these feedbacks out. Q was 0, so when we give a 0 here, we have 1 0 at the input, which means what? This NAND gate is going to give us a 1 at the output. Previously it was 1, even now it is 1. You feed this 1 back, so we have 0 1 at the input, and this is going to give us a 1 at the output. This was previously 0, and now it has changed to 1. Because it has changed, we are going to feed it back, see if this change is going to make any difference. We have 1 1 here, and when we give 1 1 here, the output is going to change to what? It's going to change to 0, right? Because the value has changed from 1, we've gone to 0, we need to feed this back to see if this is going to make any difference. We feed this 0 back, we have 0 0 at the input. When we have 0 0 at the input, this is going to give us a 1 at the output. Previously it was 1, now it is 1. So because this is not changing, we are not going to, we know that the system is stabilized now. So this is 1, and this is where we stop. So this is the final state. This is 1, and this is 0, which means what? Q is 1 and Q bar is 0. So this is a 0 for the Q. Okay, next up is a theoretical question which says, explain why the JK flip-flop is an improvement on the SR flip-flop. Okay, I've just pasted the answers from the marking scheme. Let's just quickly take a look at them and see if we understand. See, when we have an SR flip-flop can be unstable, right? It has an Q and Q bar become the same, right? So that's a problem that we have with SR flip-flop, right? The JK flip-flop does not allow for Q and Q bar to have the same value, right? So that's one of the difference. It does not become unstable. Okay, and the SR flip-flop, the inputs may arrive at different times. Remember, in a JK flip-flop, what we do is we have a clock pulse, which does what? Which synchronizes the inputs, which makes sure that the inputs arrive at the same time to the flip-flop. And finally, one more theoretical question: what is the role of flip-flops in a computer? From the marking scheme once again, but you know, let's just quickly go through this. Flip-flops can store bits, right? So they are basically used to store bits of data, and you know, they can either store a 0 or a 1, right? And they can be used as memory. So your memory can be made up of flip-flops, right? RAM, for example, can be made up of flip-flops, right? So this is basically used, a flip-flop can only store 1 bit. Remember, it doesn't store a byte, it can only store 1 bit. So if you want to store a byte, you'll need 8 flip-flops. So basically, a flip-flop is used as memory in a computer.